Hello all, welcome to the video lecture series for the subject compiler design. Now I'm here with a new topic. So this is a serial topic. We can see it is a serial process of optimization. So this is the newer one, newer variant. I can say that optimization of basic block. Okay. So let me tell you what is some example based on what is the basic blocks we have in optimization. So it is a process can be applied on a basic block while we can say that optimization we don't need to change the set of expression which was computed by a block, right? So how does this process can be done? It is done based on two different approaches. Number one, it has structured preserving transformation, right? Whichever the process you have, that should be in a structured and which can be transformed based on the preserving technique. So the second most important thing we can see that it is a algebraic transformation, right? So the first example, I'm just sticking on to this particular structured process. We can say that it has a structured process which starts with common sub-expression elimination. The same process we have seen in principal source of optimization also, right? So I am just starting with structured preserved transformation, right? So I'm just going with this. The first example I'm going with this is common sub expression elimination, right? So what does it happen? We can able to recall what we have discussed in this principal source of optimization. So here we can see that a general example I am going to take and the different one which was not discussed before, right? So for best example, this common expression elimination can be the same value which is repeated twice in different ways can be eliminated. So for example, this common sub-expression elimination is going to play a very important role in OO applications, that is object-oriented process. So now A is equal to B plus C, for example, and B is equal to A minus D. Please, you can watch this particular code carefully. You will understand before I finish this particular expression. C is equal to B plus C. You can see the repeated process here, right? Again, D is equal to A minus D, right? So here, whether you need to replace or else you need to do any one of this code elimination, that can process to be a second fourth expression computed, right? So here this is the example. I am rewriting the same code, that is A is equal to B plus C, right? Again, B is equal to A minus D, right? So we don't know what is the value D here. Okay, so D is equal to, it may have some values, right? So here you can see that D is equal to A minus D. Okay, so the A value is here. So now I am going to check whether which this code has to be replaced, but it doesn't what is it like affect any of the code in future. So generally I am having this C is equal to B plus C as it is, right? So now I am having this A minus D. A minus D is already here, so I am replacing this A minus D into B. So D is equal to B. So here I have eliminated the code in this way, in this direction or this direction, in any of the common variant, right? Because A has been replaced here, the C has been having a new value here, so I cannot replace this. So I am, instead of this, I have replaced D is equal to B, right? So this is all about how this common sub expression elimination has been adopted. Fine. So let me take you to the second step we have in this process, that is basic blocks, right? So the second process is dead code elimination. We have seen so many examples with dead code elimination. Say for example, if I is equal to 0, right? Now if this condition we have been checked, right? If I is equal to 0, then we have mentioned the value already, I is equal to 1. It is never going to satisfy this condition, right? So we can have this process also dead code. Suppose a statement, say for example, x is equal to, this case also, next example we can take. So the next example is x is equal to y plus z. Okay, so which is appears in a block, and x is dead symbol, that means it will never subsequently used. Say for example, this x is a dead one, right? So it is a dead symbol. I can say it is a dead symbol. How does this expression can be worked? Never works. Then without changing the value of the basic block, you can safely remove this statement. So this statement has to be removed. So this is one basic example I can give you for dead code elimination, right? So let me take you to the third part of it, that is renaming the temporary variables. So for example, this is a new one which we never seen in any of the previous optimization. So renaming temporary variables, right? So let me tell you how does this happen. Say for example, a statement we have, this is a statement, that is t is equal to b plus c. So this can be changed into u is equal to b plus c. Of course it can be changed where t is a temporary variable and u is a new temporary variable. This is temp and this variable is new. So we can able to see in this particular direction, right? So whatever the direction you do, whatever the approach you take, that should have a valuable approach. So here all the instance of t can be replaced. Here all the instance of t, that is b plus c, can be replaced with u without changing the block of it, right? So this process, this particular process, we are taking as renaming temporary variables. This is one kind of approach where we can rename the process, right? So this fourth approach we can see, we have an interchange of statement. Say for example, the fourth option, we have interchange. So this change you can see that of statement. Okay, so I write in short because of the time complexity. Okay, so here you can see that suppose a block that doesn't have two adjacent statements. Say for example, t1 is equal to b plus c, right? So here I am taking it that t2 is equal to x plus y. So what is the difference here? These two statements can be interchanged. These two, t1 and t2, can be interchanged without affecting the value of a block. When the value of t1 does not affect t2, this should not affect t2. So definitely we can change because it has the same name variables in different form, right? So this is all about, we can call it as structured processing of transformation. So we have seen 4 different processes in structured way. So let me take you to the next process in optimization of basic block, that is algebraic transformation. Okay, fine. So you can see that is algebraic transformation. How does it perform in optimization of basic block? So basically here you can see that any value we can change the set of expression into a algebraically equivalent set. Say for example, that's the expression. One example I can tell, right? So the process is change the set of expression into an algebraic equivalent set. Say for example, x is equal to x plus 0. Got it? So here, or else this value can be rewritten as x is equal to x, this is x asterisk 1. So what exactly it reflects? It reflects the same. Got it? So any value you compute, this can be eliminated from a basic block without changing the set expression. You can see here how does it happen. So here you can see that x plus 0 or else this can be written in different form. X is equal to x plus or else asterisk. No. So I am going with a different example here, right? Now the same process you can do in constant folding also, right? How does it happen? You can check it. Constant folding, you can check the value here, that is related optimization, right? This is the first process here. Second process here, you can check it, the constant folding, which have a compile time. We evaluate the constant and replace the constant expression. Say for example, one example, 5 asterisk 2.7. Okay, so assume that this is not a folded value, right? So would be replaced, this process, okay, that we used to call it as constant folding, can be replaced into 13.5. 5 into 2.7, that is 13.5. So this is what the algebraic transformation is really taking for. So this is a transformation of optimization. So that is the point here, right? So how does the algebraic transformation does in different form and different variables we can take. So the third example in the sense I can give you some common sub expression is generated like less than or equal to, or else greater than or equal to, and less than, greater than, or else plus, equal to, etc. So we can check all the common expression values. Sometimes the associative expression is also exposed in common sub expression without changing the basic blocks. Let me tell you some example here. So here say for example, A is equal to B plus C. Again, E is equal to C plus D plus B. Assume that this is a value. So I can intermediate this code. How does this code can be intermediated? That is having one temporary variables which makes the code more effective. So here this has been rewritten. A is equal to B plus C, for example, right? So A is equal to B plus C. Again, T is equal to C plus D. So here this process has been rewritten in this way. So E is equal to T plus D. So this is how E is equal to T plus B. The value has become, right? So this make more simplified process than the previous one, right? So we used to call this as some of the associative expression which is applied or else to expose the common sub expression without changing the basic block. Okay, if the source code have this kind of assignment statements. So this is how the process of algebraic transformation can be done, which is absolutely processed in optimization of basic blocks. Thank you.